So this is in our lab. But I'm fascinated with gravity and how it affects our performance. So now that's one of my former grad students, Rex Wu, up on the Moonwalker. The Moonwalker's back in shape. It's back up and running. Alvin is the current student to come talk to. We try to, design new spacesuits, meaning we have to understand how the old spacesuits limits people. So this is an exoskeleton, a design with Hugh Hare, the biomechatronics lab here, my lab, over in AeroAstro, taking a lot of energetic measurements, gas and how hard are you working, workload measurements, biomechanics, kind of running on force plates, and underwater experiments as well. Lots of simulations because it's rare. And when we get to really fly in microgravity, it's always wonderful when we get to. I think you'll enjoy this. I'm just going to, again, kind of show you all these different environments. Volume really makes a difference in microgravity. You'd be flying in the 0G plane. This is the Russian Ilyushin 76. This is like flying in a 747. You don't have great body control. Okay, that's what you'll recognize is you'll be a rookie when you get up there to fly. We have a lot of handlers, but you can see that it's really pretty disorienting. There's maybe going underwater is, we do a lot of simulations underwater as well, but when you get into microgravity, especially in such a huge plane like this, you really need restraints. Lesson number one, you really need restraints. Your experiments will be, strapped down and things like that, but you as a person, yes, it's fun, but you are there to do science and get great data. And so thinking about restraining everything is really important. Then sometimes you get to do a few of these. The other thing is, since have you had folks done high-G data collection?
Yeah, we had a few projects last time who wanted to.
Be interesting to see for plants and things like that. For humans, as my specialty is humans, living things. So we go over the, say, microgravity, 20 seconds. People advertise 25 seconds. I would say 20 seconds. You want to, hit your activation. You want to sync your data. So I always think about 20 seconds of pretty good 0G, parabola out of a 25-second window. You can kind of get ready when you're going through gravity up. But then you have the high G, typically a 1.8 G pullout. So depending on what you're testing, I take data the whole way through. It does make subjects, when we flew for NASA research flights, we fly like 40 parabolas. 0G kind of has it down, 15 to 20 parabolas, no one really gets sick. You can fly a little medic, and that's, so you get less science, but it's nice because, the vast majority is rare now that people get sick, so you can, do all your work. But just suffice it to say that you might want to think about data collection during the high G maneuver. So it depends on what you have automated, what you can do yourself. So again, for me, it was better to do biomechanics, energetics, really during the whole, the high G and the low G. So you might want to think about any hypotheses you have for both. And again, it's kind of short. What else? Okay, here's oldie but a goodie. This is fun. I just pulled up all my experimental. This one has music and stuff. We won't watch it. Sorry about the resolution. It's really, it's a really, really bad resolution. But that's actually astronaut Katie Coleman. A lot of that's a professional photographer, Jim Olive. Took a photographer up to, he loves seeing his. There's me. So what we're doing is posture control. We're on basically force restraints, kind of smart sensors. And we're taking a look at posture and motor control. One-armed push-ups are great, right? But so we're looking at the reaction forces, doing a whole bunch of different motions of those gold sensors, these kind of smart sensors during parabola on that again old experiments. It's really fun to fly with veterans, especially when you fly with astronauts, because I study their motor performance, and they're really pros. They literally, we've taken a lot of data, so they push off with one finger and go across the whole module, where I'm kind of a medium, I'm kind of average. I have 1,000 parabolas or more in microgravity and partial gravity, but still, I think it takes about a month of full-time spaceflight to really adapt. So you see the astronauts and cosmonauts, it's basically very low motion. It's like a finger or a toe, 10 newtons, right? And it's very low velocity. So we say fire. We had a fire on Mir, the Russian station, when my experiments were up there. But if we say fire, you guys are all going to push off really hard because you're really excited and you're going to hit the rafters, and I'm going to push off with my toe and zoop out the door, right? So there's a lot of learning that comes with, because it's just not intuitive, it's just not natural. We walk around at one body weight, and if you run, go for a run around the Charles, that's 2.5, 3 times your body weight. That's, I don't know if someone has a Fitbit on, 10,000 steps. Well, now in microgravity, it's just completely different. Order of magnitude, again, it's tens of newtons. Never hundreds of newtons in kind of any activity. So it's important for, astronaut performance, like I study, but, in the details of your experiments as well. What you can measure, how precise the measurements might need to be. You'd probably be using some, maybe videography, maybe for the plant people, a lot of video, right? You can never take enough video in real time, syncing, getting everything synced up. And it's going to go by really quickly. So that's always, that's always the case. Oh, I wish I would have done it this way and done it this way. So a lot of practice. It's definitely a lot of real-time learning. What else did I? I don't think I'll show you these. These are fun. Let's see. Here's just to show you another. This is the mirror. This is from the 90s. This is the. There's. Sound on here too, again low resolution. This is from the 90s. So that's Jerry Lininger, an astronaut. This is when we flew in the Mir space station, and again we were trying to figure out how do people perform. Well, you're not swimming, but you're very much a horizontal creature. You're no longer a biped. You don't do things upright. You kind of zoom in, and then you find a handle and you torque yourself down, kind of foot restraints to get into place. So hand restraints, foot restraints, just a lot of things to hold on to are key. And then depending on if you want to put your leg under there or your arm under there or your feet in this case. Do they make you fly? Can you wear any kind of shoes you want? Comfortable shoes?
They usually say comfy shoes or shoes that don't have a hard sole, so you don't hurt somebody else if you
Oh, because there's a lot of flailing around. And sometimes intentionally you get to the end and you might want to try to do circles and stuff like that. But yeah, it makes sense. So again, we have, and I can give you papers and things like that, lots of papers on quantifying what happens in microgravity just because it's so different than what happens in 1G. Again, orders of magnitude less in terms of the ground reaction forces, but also this very high precision control and very low velocity type of activities. Okay, so take that into stock when you're thinking about designing.
And to the mention of the papers, now you know a little bit about the projects. Whichever papers you would be interested to assign, we do readings, and so you could send.
Yeah, so it's good to when you guys get a list of a list of what the
I'll send you a note.
Exactly. I'm glad to our papers are all online, and then I think it might be kind of fun to, again, depending what you want to do, we actually called up to station and said, okay, guys, if you like physics and you like angular momentum, that this was a really fun thing. You're floating, but can I control myself with, basically my limbs? My arms are less massive, so legs work well. So we called up to this crew and said, can you guys do a pitch, roll, and yaw for us? And they did. So you can analyze them. We've modeled them. We have a lot of models on these, but these are some pretty. Each of them took a turn at doing a motion. So here's, let's see. Okay, so your arms and your legs are going, trying to control your angular momentum. So they get pretty good at it. I mean, he's not going up and down. He wants to go a little bit faster. You can practice on a bar stool. Okay, I go into bars. I don't drink a lot of beer, but I go into bars and say, okay, you guys, let's do our angular momentum experiments, right? And there's one more. Let's see. I think Ray did one for us as well.
You shared that with us last year. We did actually have some students go and practice motion on bar stools, particularly if you have like a human-based augmentation project or a suit that you want to get some intuition.
Exactly. No, this is hard. Again, you're not swimming. It kind of looks like you're swimming. There's not enough drag up there for swimming. That's Ray said, and she's an MD. But you're really again using an angular momentum transfer, if you will, to go. To kind of think about your motion. We have kind of a tutorial on how to do astronaut angular momentum trials and things like that, and we've modeled this. It's kind of fun. It's a good dynamics problem. Okay, so just a little bit more, and then I really want to take your questions, so pick my brain. I've flown 4 experiments up to first we started on the shuttle, and we did those smart sensors, those gold sensors, kind of torque sensing, just to kind of quantify the microgravity environment. The reason was to prove that the astronauts are really good at what they do, and they're not disturbing the microgravity environment. Back then, even to the Russian Mir, but definitely the shuttle, we said, wait a minute, we have humans here. What if I want to do a nice, astronomy pointing experiment? Are the humans going to disturb the microgravity specification? So we took, thousands and thousands of activities. So here's landings, here's push-ups, because from Skylab, hi, welcome. You can catch your breath and we'll catch up with you. So if you see, there's some really famous Skylab. Skylab was a huge volume. And so you see the crew pushing off with pretty large forces and zooming across the module. And then they kind of had like, Olympic trials or something. They were having fun. So you can do pretty large motions and push off. But the point is we have smaller volumes now. And plus astronauts are smart, so they don't want to disturb the microgravity environment. But we usually separate experiments. So if we're trying to do a still pointing, something with astronomy, there's not a lot of astronaut activity, especially like running on the treadmill, right? You don't want to disturb it. Because it's true that you can really disturb the microgravity environment, but typically they don't. Typically, again, singles to tens of newtons, and as a pound or two, less than 10 pounds. It's not body weights or 2 times body weights. So those early experiments just kind of proving the astronauts exert very low forces and they have pretty high precision control about their motions, especially when they get adapted. And then fast forward to Mir, when we flew with the Russians in the 90s, that was to say, well, what our hypotheses were really, can you adapt, and does it take about 30 days to do something, the real adaptation I call multi-adaptation, or dual adaptation, whereas I'm 1G, I've evolved and developed in 1G, so I'm a biped, I walk, I run, but if I spend enough time in microgravity, can I get tuned to this different, free-floating motion? So we've tested a lot of motor control, like having people, they called it darts in space, having people do, basically, it wasn't real darts, but it was a little wadded up paper 2 meters ahead of them, and then kind of see how their brain was changing their central motor system and their precision control. And again, you go and you've seen astronauts throw gummy bears to each other, M&Ms. If I take one and I throw it to Manway first, I would go really fast and it would go right up into the ceiling. Wait a minute, because, right, it's if I throw anything to you, you're going to kind of think about the dynamics, and it's going to be in an arc. It's a, Keplerian parabola. But then I said, oh, wait a minute, when I let it go, it's going to be straight line. So I have to teach myself in microgravity then this real straight line precision control motion. So that's what we were testing when we were with the Russians, because after 30 days, and sure enough, the cosmonauts who were the veterans just had amazing performance. It was like studying, an Olympic athlete. And even the NASA astronauts, there's a big difference between rookies and veterans. Even like if you've done a shuttle mission for 2 weeks or not. And then now that everyone is up 6 months on station. But I still think that it really does take about 30 days until you're kind of at that Olympic performance if you really have your microgravity. So you guys will be up there short duration. You'll get good, but as much practice as you can. And I think thinking about it, because you do want to make your motions very intentional. You definitely want to collect as much great data as you can, and making sure that you're kind of optimizing your science. And now on space station, we've had a suit that we fly, and I can just tell you a little bit about that. We work on compression suits in the lab. So one is for going out on spacewalks, but the one that's flown since 2015 to 2017, recently on the European astronauts, is just it's like kind of a one-dimensional suit, if you will. Looks like an exercise suit, like a leotard. And we're compressing the person from the shoulders down to the feet. We'd like to hypothetically put 1 G back on your feet, but it's really hard. It's not very comfortable. So we put about a half of a body weight loading. And what we do is we recompress the spinal column. Because you grow about actually 1 centimeter, 2 centimeters. Your spinal column really, so it's great. I always wanted to be taller. But most people get back pain. So we said, if we can put them in this suit and it recompresses their back, actually they don't get back pain. So we were doing it to try to first eliminate the spinal column elongation. And then they wear it when they're exercising. Exercise currently in space is a treadmill. There's 2 treadmills. There's a NASA treadmill, there's a Russian treadmill. And then there's an active resistive exercise device. It's kind of making you a power lifter. You kind of get in it and you do squats and things like that. So we're trying to reload. That's really for musculoskeletal reloading. We have a lot of deconditioning. And Then cardiovascular, typically there's an ergometer, so you can hop on the ergometer. You have to be, cinched in, or else you'd float up. You kind of cinch in the belt, and then you pedal, and you can get a pretty good cardiovascular workout that way. So those are the typical exercise devices that we use. But to last year's group, the couple students from our lab, they did a mini exercise device, because you can imagine a treadmill takes up a lot of real estate. Then you have to go over to the ergometer, and if you have 3 different exercise devices, for a mission to Mars, we're going to have a constrained volume. So what's the best exercise we can do, kind of like one exercise device, or maybe with suits. So that's kind of some of the research we're looking at is, what's the smallest and, low mass. Any of your designs, really, really low mass. That's like the key for real flight experiments, right? The less mass we can fly and take data, the better.